Hello my dear children, welcome to 𝐕𝗫𝗄 classes. My name is 𝐕𝗫𝗄. We started with a chapter from Maharashtra board class 12 chemistry halogen derivatives. In our previous video we completed the topic introduction, classification of halogen derivatives and nomenclature. Today we are going to start from preparation of halogen derivatives. Let's get started. So we completed till nomenclature part. So from here we have to start today, that is the methods of preparation of halogen derivatives, which are also called as alkyl halides. So the first method is from alcohols. Okay. So from alcohols there are different methods. The substrate would be alcohol only and the reagents will be changed according to that. There are three methods where we are going to get alkyl halides from alcohols. So the first method is from halogen halide, which are denoted by HX, and HX could be your HCl, HBr and HI. Okay, we do not take HF because normally fluorine, hydrofluoric acid shows different type of behavior. So in this case HX means HCl, HBr and HI. So alcohol that is denoted by ROH is treated with HX here in suitable condition, because the condition will be changed that we are going to see later. So here it will be RX, this OH will be substituted by X. Okay, this OH will be substituted by X. So we are getting RX here and H and OH will come out as water. So I will show you like this. This is your OH and H is come out as water. So RX is your alkyl halide and H2O is come out as water. So when we are using HCl in case of HX, we are using HCl. This primary alcohol is reacted with hydrochloric acid in presence of anhydrous ZnCl2. This is very important. It gives primary alkyl chloride. So our primary alcohol is RCH2OH. This is our primary alcohol, is reacting with HCl in presence of ZnCl2. Anhydrous ZnCl2 has to be taken here. Again, the role of Cl is what? To reduce or to replace this OH by Cl. So it will be RCH2Cl and H2O will be coming out as water. H2, how H2 is coming out? Like this. H from here and OH from here coming out as water. So we are taking an example CH3CH2OH, which is called as ethyl alcohol. It's an alcohol with two carbon atom reacting with HCl and anhydrous ZnCl2. We are getting CH3CH2Cl. So basically OH from here and H from HCl is coming out as water. Okay. I hope everybody understood. You can take a screenshot. Yes. Let us move on to the next one. This is a secondary alcohol, CHOHR. Everybody knows that CHOH means it's a secondary alcohol treated with HCl and anhydrous ZnCl2. We are getting RCHClR and H2O. So basically this OH is getting substituted by Cl. In short, if I say the role of this reagent is to substitute OH by Cl. That's all. Here, this is a general specific example of secondary alcohol, that is CH3CHOH which is isopropyl alcohol. This group is called as isopropyl group. Isopropyl alcohol, which is a secondary alcohol treated by HCl anhydrous ZnCl2. So you can see the OH is substituted by Cl. So we get isopropyl chloride and the byproduct is water. Now here HCl and anhydrous ZnCl2, this mixture is called as Lewis reagent. Very important. The mixture of HCl and anhydrous ZnCl2 is known as Lewis reagent. 1 degree alcohol and 2 degree alcohol plus HCl. This process is called as Group's process. So till now whatever examples we have taken, this process is called as Group's process. Now if you have a 3 degree alcohol R3COH, you can see this is a 3 degree alcohol plus HCl will give you 3 degree alkyl halide plus H2O. Okay. So this is the first method of by using HCl. Now this is the example of 3 degree alcohol. This is tertiary butyl alcohol. 1, 2, 3, 4. It's called as tertiary butyl alcohol. HCl, you are treating with HCl, the OH is substituted by Cl. So you are getting tertiary butyl chloride plus water molecule is coming out. Next is the reactivity of this is alcohol, 3 degree alcohol will be reacting much faster than 2 degree and then 1 degree. So this is the reactivity of alcohol, and the reactivity of haloic acid is HI, HBr, HCl and HF. They have taken HF here, but we have not shown any of the reaction with HF. Why this is so? Because HI, if you see, the size of iodine is bigger. Size, if you see, then iodine is bigger than Br, which is again bigger than chlorine and which is bigger than fluorine. So when you talk about HI, the bond length will be much more bigger than HBr, and which is against HCl will be smaller and HF will be very small. So if the bond length is bigger, we know that bond length is inversely proportional to bond strength. So if the bond strength here, so if the bond length is bigger, that means the bond strength is small, and that is why I will be the bond will be broken easily in this case. Okay, so that is why the reactivity of haloic acids are this way. Now using HBr. Now the way we have taken HCl directly, we cannot take HBr directly. We have to produce HBr in situ. In situ means inside the reaction mixture. So how do we do it? We basically add NaBr and H2SO4. This is H2SO4. I have written it this way. It is basically H2SO4. H and H is H2SO4. So sulfuric acid. So NaBr plus H2SO4. Na will be substituting one of the H. So it will give you NaHSO4. Okay, and this H and this Br togetherly will give you HBr. So this is how we are going to produce HBr, which is our reagent in situ. So basically we are going to add the 1 degree alcohol. This is 1 degree alcohol, and we are going to add NaBr plus H2SO4, which is giving rise to this HBr, and then HBr will be reacting with this. Again here also same thing, OH and H will be coming out as water, and Br will substitute this OH. So we are getting RCH2Br plus H2O. That is from 1 degree alcohol we are getting 1 degree alkyl halide. This is a 2 degree, this is ethyl alcohol. Okay, so this is a particular example of 1 degree alcohol, ethyl alcohol plus HBr. Again HBr is produced by NaBr plus H2SO4, and this OH will be substituted by Br. So we are getting CH3CH2Br. This is secondary alcohol, RCHOHR, secondary alcohol. We are treating with HBr. HBr is coming from here, NaBr plus H2SO4. Here this OH will be substituted by Br. So Br can see RCHBrR. So this is 2 degree alkyl halide plus water. So when isopropyl alcohol is reacted with hydrogen bromide, now we have taken a particular example, isopropyl alcohol, which is a 2 degree alcohol, is treated with hydrogen bromide in presence of sodium bromide and sulfuric acid. So hydrogen bromide we directly do not get, we have to add in NaBr plus H2SO4, and it gives isopropyl bromide. So the product what we are getting is isopropyl bromide. Concept is again same, HOH comes out as water, and in short you can just remember that OH will be substituted by Br. Wherever the OH is, it will be substituted by Br. So you get this product. Now this is 3 degree alcohol, RCRROH. This is a 3 degree alcohol plus HBr. You can see the OH is substituted by Br. So we have taken a particular example, tertiary butyl alcohol plus HBr. HBr comes from here, and we get OH substituted by Br. So we get tertiary butyl bromide plus water. I hope this is clear till here. We have used HCl, we have used HBr. Now we are using HI. HI also can be prepared in situ by the reaction of NaI plus H3PO4. NaI plus H3PO4, Na will be replacing one of the hydrogen from here. This is H and H2PO4 you can consider. So this H and I will give you HI, and the other product will be NaH2PO4, this one. So HI we are getting this way. HI is the main reagent. Okay, so now this is your primary alcohol, CH3CH2OH. We have directly taken ethyl alcohol. HI is the reagent which is coming from NaI plus H3PO4. This OH and H will be coming out from here, and I will get added. So we are getting ethyl iodide, CH3CH2I plus H2O. Here, this is your secondary alcohol CH3, CHOH, CH3 treating with HI. Again, this OH will be substituted by I. Okay, just in short, you need to remember wherever the OHs will be substituted by I. So you are getting isopropyl iodide. The byproduct is water. Okay, so the second preparation will be by using PCl3. Here also our substrate is alcohol only, but we are using PCl3. So it is like this. I am taking the primary alcohol first, RCH2OH. This is my 1 degree alcohol, and this I am treating with PCl3. What happens, see, this OH will be substituted by chlorine. Okay, so you will be getting RCH2Cl. Now see, here 3 chlorines are there. So if I have to balance this, this will be 3 chlorine, but again RCH2 part has become 3. So I will add 3 over here. Now see, this OH is coming out. That means 3 OH has come out from here and 1 P come out from here. Okay, 3 OH has come out from here and 1 P has come out from here. So these 3 together will give you H3. Then I am writing P and then O3, which is your phosphorus acid. So here the byproduct is H3PO3, which is called as phosphorus acid. I hope everybody understood how the balancing has been done. So this is your 1 degree alcohol, and here you are getting 1 degree alkyl halide. Okay, so if I take a particular example, suppose CH3CH2OH. This is my example. This is called as ethyl alcohol, and this I am treating with PCl3. So first of all, I will be getting this OH will be substituted by Cl, CH3CH2Cl. Now there are 3 Cl, so I will make it 3. So I will make this 3, and then I will be writing the byproduct as H3PO3. So this is with your primary alcohol. Now similarly, if I take a secondary alcohol, I write RCHR and CH3. This is RCHOH, sorry, this is OH I will write because I have written over it. Okay. So this is your OH, RCHOH, and this also I am writing R only. I am taking a general secondary alcohol, RCHOHR, and this I am treating with PCl3. So wherever the OH is, here you have to substitute by Cl. So it will be RCHClR plus H3PO3. So this is again the same thing. This will be 3, this will be 3, and H3PO3 is a byproduct. This is a secondary alkyl halide. Okay, so this is a second reaction. I hope everybody understood here. I'll just go back to the slide now. Yeah. So this is my particular example of secondary alcohol, isopropyl alcohol, and this is treated with PBr3. Achha. Now this is by using HBr. This slide is actually missed, so I'll write one more slide here so that you understand. Okay, so this part I think everybody clear with. Now if I use PBr3 here, this one is PBr3 now. Okay, so this is your PBr3. But PBr3 cannot be produced and kept it because it is an unstable compound. So we have to prepare PBr3 in situ. How? That is by P4 plus Br2. By the reaction of these two, we will be getting PBr3. Now, if I suppose write it here 4, so this is P4, so 4 PBr3, so 4 3s are 12 bromine, so it will be 6 Br2. So by the addition of red phosphorus and bromine, we get PBr3. PBr3 has to be produced in situ because it is an unstable compound. Okay, so now this reaction can be written as, I'll just rub this part. So here I'll be taking a 1 degree alcohol, okay, and now I'm treating this with PBr3 for the preparation of bromoalkane. The PBr3 is coming from P4 and red phosphorus and Br2. Okay, same thing will happen. This OH will be substituted by Br. So I get R CH2. OH will be substituted by Br plus H3PO3. For balancing purpose, I'll write a 3 over there. So this is your 1 degree alkyl halide again, or you can say alkyl bromide. 1 degree alkyl bromide. So if I take a particular example, here PBr3, and this PBr3 will be coming from P4 and Br2. So this will be CH3CH2Br plus H3PO3. So this is your 3 and this is your 3. Yeah, so ethyl alcohol, from ethyl alcohol we will be getting ethyl bromide. From ethyl alcohol we are going to get ethyl bromide. Now we'll go back to the next previous slide. Yeah, so now here it is a isopropyl alcohol, which is a 2 degree alcohol. This is a 2 degree alcohol. We are treating this with PBr3. Again, PBr3 is coming from P4 and Br2. The OH will be substituted by Br, that is isopropyl bromide we are getting, and the byproduct is H3PO3. Similarly, if we are using Pi3 for the preparation of iodoalkane or alkyl iodide, okay, Pi3 also unstable, we cannot prepare and keep it, so we have to prepare in situ by the preparation of phosphorus and I2. Again the same thing, P4 plus 6I2 will give us 4Pi3. So Pi3 will be produced in situ by the action of red phosphorus and iodine. So here this is my 1 degree alcohol. We have taken ethyl alcohol directly, treated with Pi3, which is coming from P4 plus I2, and this OH will be substituted by iodine. So here you can see this OH is substituted by iodine. We are getting ethyl iodide. Here this is by using now, next we are using phosphorus pentachloride. This is a next method. The substrate is still alcohol, but we are using the reagent as phosphorus pentachloride. So this is my alcohol ROH. I am treating this with PCl5. What is happening? This OH will be substituted by one of the chlorine. So we got RCl. Okay, now after this OH is substituted by one of the chlorine, what is remaining? See, this OH is coming from here, which is remaining, and from here PCl4 is remaining. So one hydrogen and one Cl you take to form HCl. Now what is remaining? 1 P oxygen and 2 chlorine. So that is 3 chlorine. So that is giving you POCl3, which is called as phosphoryl chloride. Again I will tell you, I hope this is again, see the balancing how it is happening. This OH is substituted by one chlorine. So this OH has come out, and from here P and Cl4 is remaining. So this H you take and one of the chlorine you take to form HCl. Okay. So now remaining PO and Cl3. So that is giving you POCl3, which is phosphoryl chloride. So this is how it is happening. So the role of PCl3 and PCl5 is the same. That is to substitute OH by the halogen, that is chlorine. But the byproducts are different. So you are getting RCl plus POCl3 plus HCl. POCl3 is called as phosphoryl chloride. We have taken a particular example, ethyl alcohol plus PCl5. So this OH will be substituted by, OH will be substituted by chlorine. So you are getting CH3CH2Cl, which is ethyl chloride plus POCl3 plus HCl. Now note that PCl5 exists. It is a stable compound, but PBr3 and Pi3, they does not exist. They are unstable. They do not exist, and that is why we will not do the reactions with PBr3 and Pi3. Okay, PBr5 and Pi5. Okay. Now the next thing is from thionyl chloride, SOCl2, and this method is called as Darzen method. Again our substrate is same here, that is alcohol, but now we are treating alcohol from thionyl chloride, that is SOCl2. So ROH plus SOCl2, the solvent is pyridine here, we are refluxing it, and this OH will be substituted by Cl. So we are getting RCl. This H and this one of the Cl will give you HCl, and S and 2 oxygens are remaining, which are giving you SO2. So basically OH is coming out from here, and SO and 1 Cl is remaining. So this hydrogen and chlorine will give you HCl, and SO and O will give you SO2. So this is the thing. Okay, so this method is called as Darzin's method, and this whole thing you need to remember. So we are taking ethyl alcohol CH3CH2OH plus SOCl2. We are defluxing it in presence of pyridine. OH will be substituted by Cl. So we are getting ethyl chloride plus SO2 and plus HCl. This method is preferred over all the previous methods we have studied, because see here it is written, this method is the best method to prepare alkyl halide, because the byproducts formed is in gaseous form. SO2 and HCl, both the byproducts are in gaseous form and they will escape out. So you don't have to put any extra effort to separate the byproduct from the main products, and hence this method is very, very useful method, and it is best over the other method also. But another thing is, by this method you can only prepare chloroalkane or alkyl chloride. Bromoalkane or iodoalkane cannot be prepared by this method. Come to the next method of the preparation of haloalkane, and the next method is from hydrocarbons. Okay, so there are two hydrocarbons from where we are going to prepare haloalkane. One is from alkane and the other one will be from alkene. So first we are going to see from alkane. From alkane we are producing it by addition of halogen. So this is my alkane, RH. Everybody knows how to write down alkane. This is a general formula for alkane. We are treating this with halogen. It can be Cl2, Br2 or I2 in presence of UV light. So one of the hydrogen will be substituted by one of the halogen. So this will be Rx, and this hydrogen and other X will give you HX. So this is the method. Okay, we have taken ethane here. Chlorine is present. So in presence of UV light, you are getting CH3CH2Cl, that is ethyl chloride and HCl. One of the hydrogen, if I write it this way, suppose if I write it this way, this is CH2 and H. If I write ethane like this, then what happens is, also I am writing chlorine this way. Chlorine this way. Now I can show you this HCl is coming out and you are getting CH3CH2Cl. So HCl is a byproduct over there. Come to the next one. This is propane. Okay. Now see, in propane we have got two different types of hydrogen. One is this hydrogen. This hydrogen, if I call it as A, CH3, and if you see this CH3, they are same. So this is also A. But this hydrogen is different, so I call it as B. So there are two hydrogens, and both the hydrogens are, they can be substituted by bromine. So if this hydrogen B is substituted by bromine, we get CH3CHBr CH3, which is your isopropyl bromide. And if this one is substituted or this one is substituted, it's the same thing. Then we get CH3CH2CH2Br, which is N-propyl bromide. The byproduct is again the substituted hydrogen, and another bromine will give you HBr. Okay, so we get two products here. This is major and this is minor. Now, why this is major? See, this is actually a photochemical reaction. Any reaction which happens in presence of light, that is a photochemical reaction, and most of the photochemical reaction goes through free radical mechanism. Okay, so here one free radical will be generated. So here, if you see this, if you break this bond, the free radical here will be a secondary free radical, and if you break this bond here, the free radical will be a primary free radical. And the secondary free radical are always more stable than the primary free radical, and that is why the generation of secondary free radical will be more, and hence this will be the major product. I am not going into the detail of it. You just remember that the tertiary free radical, 3 degree free radical is more stable than 2 degree free radical, and which is more stable than 1 degree free radical. It is just like carbocation. Okay, the stability of free radical and carbocation, the degree is same. 3 degrees more stable than 2 degree than 1 degree. So here there is a 2 degree free radical and this is a 1 degree free radical. So this will be more, and that is why the product also will be more. So you have taken a particular example here. Oh, okay. This is a tertiary isobutane. Isobutane. Actually, we have taken a isobutane. CH3, 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 CH3. This is isobutane. and chlorine, you are reacting with chlorine in presence of UV light. So how many types of hydrogens are there? This is one type A, this is also same, and this is also same. So this is A type of hydrogen and this is B type of hydrogen. So if this B is substituted by chlorine, you get this product, okay? This product, which is tertiary butyl chloride. And if A is substituted by chlorine, you get this product, which is your isobutyl chloride. Now again, if anyone asks you which one is the major product, again this is the major product, because if you break this bond, you can see this is a tertiary free radical, and break this bond, you can see again this is a primary free radical. So this will be the major product. Okay. Yeah. Now this is the reaction of methane with chlorine in presence of UV light. Since it is a free radical mechanism, the reaction will not stop as it is. You have to terminate the reaction, because I think you know that free radical mechanism goes via 3 steps. The first step is initiation, second is propagation, and third one is termination. Once the reaction is initiated, you can't stop it. It is a chain reaction. So in case of methane, what happens? See, first one of the hydrogen is replaced and you get methyl chloride. Now this methyl chloride again will react with chlorine. Again another hydrogen will be replaced and one chlorine will be introduced. So you get CH2Cl2. And again this CH2Cl2 reacts with Cl2. One of the hydrogen reduces, one chlorine increases, you get CHCl3, and finally CHCl3 reacts with chlorine and you get carbon tetrachloride plus HCl. So basically it is this way. There are 4 replaceable hydrogen in methane. This is 1, 2nd, 3rd and 4th. So when you are reacting with chlorine in presence of UV, so since it is a photochemical reaction, first this hydrogen is replaced by chlorine and you get a product like C, H, H, H and Cl plus HCl. Now again this C, H, H, H and Cl, this will be reacting with another molecule of chlorine. Now this hydrogen will be replaced. So here one chlorine will come and you will be getting C, H, Cl, Cl, H plus HCl. So this is how the reaction will go on as long as all the hydrogens are not replaced by chlorine, and you finally get a product that is CCl4. Basically, the production of haloalkane from alkane is not a very useful method, because you can see there we are getting a mixture of compounds, and if you want a particular product, the yield or the amount of the compound will decrease since we are getting a mixture of compound. And the other thing is it's very difficult to separate them also, because those are isomers are getting created or getting formed. So it's very difficult to separate the isomers, because they differ by their physical properties in a very very small differences there. So it's very difficult to separate them out. So that method is not a very important method or suitable method for the preparation of haloalkane from alkanes. Now the second method from hydrocarbon is from alkene, and this is by addition of hydrogen halide. So first is using symmetrical alkane. There are 2 types of alkane, symmetrical or unsymmetrical. In symmetrical alkane we have taken ethene and we are reacting with HCl. So HCl will just get added across the double bond. One of the carbon will contain H and one of the carbon will contain Cl. So you are getting CH3, CH2, Cl. So here whether chlorine is getting attached to this carbon or this carbon doesn't matter, you get the same compound because it's a symmetrical alkene. For symmetrical alkene like 2-butene or but2ene, you are adding HBr. So one of the carbon is containing H and the other carbon is containing Br. So you are getting secondary butyl bromide or 2-bromobutane like this, okay? But, and this is using unsymmetrical alkene. When the same reaction is happened using unsymmetrical alkene, then we have to follow the Markovnikov's rule. What is this rule? Very, very important. It says that the negative part of the reagent, that is, this is a negative part and this is a positive part. The negative part of the reagent will get attached to that carbon atom which is having less number of hydrogen. Let's see when unsymmetrical reagent is added to unsymmetrical alkenes, okay? So the negative part of the reagent gets attached to that carbon which contains less number of hydrogen atom across the CC double bond. So this is your Markovnikov rule. Let us see the example here. When unsymmetrical alkene is added with hydrogen bromide in presence of peroxide, okay? You are adding hydrogen bromide in presence of peroxide, then Acha, then the anti-Markovnikov rule will take place. Okay, so here we are talking about the anti-Markovnikov rule. So in presence of peroxide, if you are doing the addition, then the reverse of Markovnikov will take place. That is the negative part, the bromide, and that's the negative part will get attached to that carbon atom which is having more number of hydrogen. This is called as anti-Markovnikov rule. Okay, this is opposite to Markovnikov's rules, and hence it is called as anti-Markovnikov rule. And this was studied by 𝐏𝐻 and Mayow, and that is why this is also called as 𝐏𝐻 and Mayow effect. The other name of this reaction is peroxide effect. So all of these are the other name of anti-Markovnikov rule. So here see, this is the alkene, unsymmetrical alkene. Now first I will show you the Markovnikov rule. Suppose I have unsymmetrical alkene like CH3CH double bond CH2. This is propene, which is unsymmetrical because across the double bond the alkyl groups are different, and you are adding HBr. Okay, so HBr, this is the Br is the negative part. So the negative part will get attached to that carbon atom which is having less number of hydrogen. This is Markovnikov rule. So across the carbon-carbon double bond, you see this carbon is having only one hydrogen and this is having two hydrogens. So Br will get attached to this carbon. This is your normal Markovnikov rule. CH3 CHBr plus hydrogen will get attached to this carbon. So you will be getting 2-bromopropane as a major product in the case of Markovnikov. But the same reaction, if it is done in presence of peroxide, okay, then anti-Markovnikov will take place. That means the Br will get attached to this carbon and H will get attached to this carbon. So you will be getting CH3, CH2, CH2Br, that is 1-bromopropane. Okay, now here note, anti-Markovnikov rule is applicable for HBr only. If you put here HCl or HI, the reaction will be not applicable. So it is only applicable for HBr. Okay, now we come to the next reaction, that is by halogen exchange. In this we have to study two reactions, and both the reactions are named reactions, very important. The first reaction is Finkelstein reaction, where alkyl halide, halogen exchange it is. So your substrate is alkyl halide and you are treating that with NaI with dry acetone. Whenever you say NaI and dry acetone, you understand it is Finkelstein reaction. What happens is this X will be substituted by I. Okay, so this X can be chlorine or bromine, and that is substituted by I. So you get Ri plus NaX. So I can say that this is a very particular reaction, or exclusively this reaction is for the preparation of alkyl iodide. Okay, so here CH3Cl I have taken methyl chloride and it is treated with NaI dry acetone. Cl is substituted by I, so you get CH3I plus NaCl. Okay, similarly here CH3CH2Br, that is ethyl bromide you have taken, and NaI in presence of dry acetone you are getting this Br will be substituted by I, so you get ethyl iodide. This is your Finkelstein reaction, which is an exclusive reaction or exclusive method for the preparation of iodoalkane from bromoalkane or chloroalkane. Now the next named reaction is Schwarz reaction. This is also similar type where we are going to produce alkyl fluoride. Now this is the first method. So far we have not produced alkyl fluoride at all. This is the first method where we are going to produce alkyl fluoride. So our substrate is again Rx. This X can be chlorine or bromine. And you are treating that with AgF, okay, and this AgX will be coming out and you are getting Rf, which is your alkyl fluoride. Okay, so this is methyl chloride treating with AgF. You are taking out AgCl, we are getting CH3F, that is methyl fluoride plus AgCl. This is ethyl bromide and this AgBr will be coming out, so you are getting ethyl fluoride plus AgBr. This is propyl chloride treating with AgF and you are getting propyl fluoride plus AgCl. Note that this reaction can also be done with the presence of Hg2F2, SbF5, SFF3 are also used in Schwarz reaction. So this also could be the reagent in place of AgF. Okay, so this is your Schwarz reaction. So with the Schwarz reaction we have completed all the preparation of haloalkane. Now we are starting with the preparation of haloarene. What are haloarene? I hope you remember, when the halogen atom is directly attached to the aromatic ring, then it is called as haloarene. Okay, so this is prepared by, first method is addition of bromine on toluene. What is toluene? Toluene is CH3 attached to benzene ring. This is called as toluene. You react bromine in presence of Fe and the reaction happens in dark only. Okay, Fe acts as a Lewis acid here basically. It takes out one bromine from here and it creates a bromine plus Br plus electrophile. Okay, so this is an electrophilic substitution reaction. I'm not going to the detail because here we are actually revising the things. So toluene with reaction with bromine in presence of Fe, bromine will get attached to the ring or it will get introduced to the ring. Now toluene CH3 group is a ortho-para directing group. So the Br will get attached to para position and in the ortho position, para will be always the major product. Okay, so it is 4-bromotoluene which is major and 2-bromotoluene which is minor. So this is the first method, and the second method is again a named reaction which is called 𝐶-Meyer's reaction. What is this? The replacement of a diazo group. Here one diazo group is replaced by chloride or bromide. Using 𝐶𝐤𝐝 salt is called as 𝐶-Meyer's reaction. This is the definition of the reaction. Now what is happening? See, this is benzene diazonium chloride. On the benzene ring, if you have N2 plus and Cl minus, this is called as benzene diazonium chloride. This is treated with CuCl Okay, CuCl and this entire N2Cl group is substituted by chlorine. You are getting chlorobenzene. The byproducts are nitrogen and HCl. Okay, here the same thing. If you treat with CuBr and HBr, the entire N2Cl group is substituted by bromine. You are getting bromobenzene plus nitrogen plus HCl. So this is your 𝐶-Meyer's reaction. And okay, so this was that Markovnikov. This has come wrong actually. Okay, so the entire thing, if I summarize the preparation, how it will be, I'll just summarize it. Preparation of haloalkanes. So the first preparation was from alcohol. From alcohol we had three preparations. The first one by using HX, okay, and second one is PCl3 or PCl5, and the third one is SOCl2. By using HX here we had three methods. I should write it this way here. Using HX, and in HX we have got three. One is using HCl for the preparation of fluoroalkane, using HBr for the preparation of bromoalkane, and using HI for the preparation of iodoalkane. Now from when we are using HCl, we are using HCl plus ZnCl2. This mixture was called as Leucas reagent. HBr we used NaBr plus H2SO4 to prepare HBr, and for HI we used NaI plus H3PO4. Okay, so this all we need to remember. Next is PCl3 and PCl5. These we used, and SOCl2 we used. This method we called it as Darzin's method. Okay, so this was the first preparation. The second preparation was from hydrocarbon. So here also we have seen two methods. One is from alkanes by the substitution method using UV light, and the other one is alkenes. Okay, now here we have studied the Markovnikov and anti-Markovnikov rule, which is very important. I'll just write it here. The Markovnikov rule and the anti-Markovnikov rule, AMR, which is very important, so we need to remember this thing. The third preparation was from halogen exchange. So this, in halogen exchange we have studied two reactions. One is the Finkelstein reaction, and the other one is the Schwarz reaction. Schwarz reaction. Finkelstein reaction was specifically for preparation of iodoalkane, and Schwarz reaction was specifically for the preparation of your fluoroalkane. Now in Finkelstein the reagent was NaI plus dry acetone. This was the reagent in Finkelstein, and in Schwarz reaction the reagent was either AgF or Hg2F2 or SbF5 or AsF3. These were the reagent for Schwarz reaction. Okay, so this is the entire preparation of haloalkane. So you need to prepare it this way. Once you study the entire thing, then you prepare your own flow chart so that you remember. Here also you can write down the reactions and just remember the general reactions, or you can take one example, specific example, and remember the entire preparation method. So here we completed with the preparation method of haloalkane and haloarene. In haloarene preparation you don't have much. You have only two reactions. One is electrophilic substitution reaction and the other one is Sand-Meyer's reaction. Sand-Meyer reaction is important because that's a named reaction, and wherever you get named reaction in organic chemistry, they are important. You get most of the questions coming from named reactions only. So you need to very nicely remember the substrate, the reagent and the product for each and every named reactions. Thank you so much. We will stop the video here only today. In the next video, we are coming up with the physical properties and the chemical reactions of haloalkane. Thank you. If you are finding these videos are beneficial for you, please subscribe the channel and press the like button. Stay tuned. Thank you.